In this video, I will review the radical functions, and I'm going to follow the following template that we developed in one of the earlier videos called precalculus review. First, we're going to review the prerequisites, and then we will answer the questions in each of these rows. If you need to refresh your memory on what each of these questions represents, please watch that precalculus review video. And let's get started. And first, let's talk about operations. So when it comes to radical functions, it's very natural that you have to be comfortable with radical operations. But we also have to remember that radicals are exponents. So nth root is the same as raising a number to the power 1 over n. So you should be able to compute reciprocals as well. When it comes to expressions, you should be able to, again, naturally, we have this progression from radical as an operation to radical as a function, and in between we have radical expressions and radical equations. So of course you have to be able to simplify radical expressions and solve radical equations. Now, a radical equation in general may look like this, but the definition of a radical equation is as such that can be written in this form for some expression inside of the radical and some number on the right-hand side. Now, to solve this radical equation depends, how you solve this radical equation depends on this number and the index in the of the radical. So if the index is even, so you have like some even root of some expression equals to a negative number, that's impossible. Therefore, the solution doesn't exist. However, if the right-hand side is positive or equal to 0, then you can solve that equation by simply raising both sides to the power n. Now, when n is even, we don't have an issue because nth roots of negative numbers do exist. So it's not a problem. So to solve this equation, we simply raise both sides to the power n. Again, remember, it only works and makes sense when n is odd. Now that we have done the conversation about the prerequisites, we can move on and start answering these questions. So let's start with the form. A radical function can be written what we can refer to as a vertex form by analogy to a vertex form of absolute value equation or parabola or quadratic, which is the same as a quadratic equation. However, when you set h and k equal to 0 and a is equal to 1, you end up with the simplest radical function that looks like this. Now, you should know how to graph the simple radical function with the coefficient in front of it. So all of that depends on the index n, whether it's even or odd, and the sign of the coefficient a, whether it's positive or negative. So here I have an example of a graph with a positive a and even n. So you see this pattern, it starts at 0, 0 and goes up to the right. If you have odd n but positive a, it doesn't start at 0, 0, but it kind of goes through to the negative bottom left quadrant. So it has this shape right over here. Now, the other combinations are a is negative, n is odd. So it looks like this. And the last one is when you have, what is this one? I think I'm missing one here. The other one will be when you have a negative a and even n, then it's just gonna be like the graph starts here and goes to the bottom right quadrant. Now, when you add some, I have a wrong slide over here. When you add some coefficients h and k here, according to the linear transformation rules, all it does is just shifts the origin to h and k, to the point with coordinates h and k. So to graph a radical function of this form, you pretty much take the parent function and just shift it h to the right and k up units. If k is negative, you go down. If h is negative, you go to the left. Now, despite of all these linear transformations, you'll never have to do a horizontal compression or stretch to a radical function because of the property of the radicals. The coefficient of x can always be factored out of the radical for odd values of n, and for even values of n, you can take out the absolute value of it and keep the sign inside of the radical. So for example, instead of graphing this function, which requires 1, 2, 3, 4 transformations, you can just graph this function, which only requires 3 transformations, which is nice. Now that you have the graph of a function in front of you, you can start discussing its domain and the range. Domain of a radical function depends on the value of n. If n is odd, then domain is all real numbers. There are no constraints. You can put negative numbers inside of the cube root or 11th root. However, if n is even, then what's inside of the radical must be greater than or equal to 0, which creates a constraint, and that constraint kind of creates your domain. So x, in this case, x has to be greater than h. So your domain is all the numbers above h. If you have h minus x inside here, then it's going to be all the numbers to the left of h, including h. Now, the range also depends on whether n is even or odd. If n is odd, then range is always all real numbers. If n is even, then again, it all depends on the value of k and the direction in which that curve opens up. So for example, in this case, your range will be from 0 to infinity, but when it's upside down, the range extends to the negative direction, starting at that largest value. Again, this summarizes all that knowledge. Now, when it comes to intercepts, there's nothing new. To find the y-intercept, you have to set x equal to 0, and to find the x-intercept, you have to set the y equal to 0. So setting the x equal to 0 pretty much takes you back to the arithmetic. You just simply have to evaluate this expression. However, setting f of x equal to 0 takes you to algebra, meaning you have to now solve this equation, which may not always be possible. So only when n is odd, you have both the x and y intercepts. When n is even, you may not have neither x nor y intercept. So it really depends on the combination of numbers that you are given. It's important to remember that radical functions do not have asymptotes. It is important to remember that radical functions are continuous in their domain. So when n is odd, it's all real numbers. When n is even, it's whatever that graph starts, that's where it continues. It doesn't have discontinuity points, but it does have points at which the graph is not defined. So you just need to remember that, and not to say that radical functions are continuous on the entire real number line. That's not true. Monotonicity, it's simple. Graphs of radical functions are always either increasing or decreasing, and it all depends on the value of a. If a is positive, it's always increasing. If a is negative, it's always decreasing on its domain. Because of that, so since the graphs of radical functions are monotone, that means they are also one-to-one. And as all one-to-one functions, they have inverses. So if you're looking for an inverse function of a radical function, you have to follow this procedure. And here's an example of finding an inverse function to a radical function in this form. As a result, you get a power function shifted horizontally and vertically. And if n is even, the power function's domain is restricted to the values depending on what's in your integrand. It could be restricted to the values x greater than or equal to k, or it could be restricted to the values x less than or equal to k. All right, the goal here is not to memorize this, but to just understand all the relations. Now, radical functions, when n is even, do not have a symmetry because you're just dealing with one branch of it. But radical functions when n is odd and when the vertical shift is 0 are actually odd, meaning they have the symmetry with respect to the origin. What are the special features of radical functions? Well, they are inverses of power functions, so they kind of inherit some of those properties, but like inversed. So uh, power functions are important because they are basic polynomials. Polynomials are important because they're flexible, and kind of radical functions kind of inherit that little vibe of being important. Now, when it comes to finding radical functions given points, the rule of thumb still applies. If you have 3 parameters, you have to have 3 points. But the type of equation that you end up with are nonlinear, and we're not really that concerned with solving systems of nonlinear equations in algebra. So you probably never seen a problem like this, which is totally fine. From the theoretical point of view, it's not really a complex task. Now, when it comes to applications, just like with special features, the radical functions are mainly relevant in the context of their siblings polynomial functions, or rather power functions and their siblings polynomial functions, and their applications. So sometimes when you're working with a power function that is one-to-one, you may want to find its inverse, and then the inverse is a radical function. So that's the only application I can think of, like theoretical kind of application, but I'm pretty sure there are some practical applications that require the use of a radical function. For example, discriminant in a quadratic formula has a radical. So radicals are important, and therefore radical functions are also important. So this concludes the review of radical functions. And the format of this review didn't allow me to go into too many details. So if you need more details for any of the slides, please let me know in the comments below.